everyone, and thank you for joining us this morning for the final session of the Digital Summit with a New Winter Approach. I hope you've enjoyed the session so far, but if you have missed any, the recordings are available on the website for you to view. I'll be running the first part of today's winter weather workshop with MetDesk. MetDesk provide the winter maintenance forecast to highways authorities across the UK. However, we do also provide forecasts to energy, rail and construction sectors too. Some of you may recognise me, whilst others I might be a new face. So my name is Cassie and I'm one of the account managers at MetDesk. I've been at MetDesk now for 5 years, although originally I did start at MetDesk as a forecaster before moving over to the commercial team. So you might have seen my name crop up on your forecast too before now. So what does MetDesk's winter weather workshop have in store for you? I'm going to start the session off by talking about cloud cover and model uncertainty, followed by a couple of mock marginal scenarios and things to look out for. After that, our forecast manager Brendan Jones will be joining us to give an update on the long-range forecast and what might be in store for us over the coming months. Finally, I then welcome you to join myself and my colleague Richard Hogg for a live Q&A session. So, cloud. Cloud is the single most important influence on the road surface temperature, and this is what I'm going to be talking about first before we move over to the scenario. So as I said, cloud is the single most important influence on the road surface temperatures. However, it is also one of the most difficult indices to predict, as it can vary dramatically hour to hour and place to place. Low cloud is the most effective at keeping nighttime warmth, as it acts like a blanket to the outgoing heat. However, low cloud is localized and therefore is very difficult to forecast. Then you've got convective cloud and also layer cloud. Convective cloud is usually localized and caused when air is warmed and rises through convection, and this tends to be just a few miles across, whilst layer cloud is formed by large-scale ascents of air across whole countries. So this is more widespread than convective cloud and can be hundreds or even thousands of kilometres long. So forecasters at MetDesk look at several model outputs. Here we're going to look at 4 model outputs on the same day at the same time. So as you can see straight away, each model is suggesting various amounts of cloud. And as I previously mentioned, the cloud cover is single most important influence on the road surface temperature. So let's, in this example, put ourselves in the West Midlands. So as you can see in the top left-hand example, the model output is suggesting overcast conditions. So at this time of year, at the end of the night, so around dawn time, you'd be expecting road surface temperatures to remain above zero under cloudy conditions. Whereas in the top right, if you were to get this model, you'd be looking at clear skies across the West Midlands. But obviously, road surface temperatures would more than likely be below zero under clear skies at this time of year. Again, similarly, the bottom left has clear skies, so you'd expect road surface temperatures to be below zero in this particular scenario. Whilst the bottom right, you can see that there's partially cloudy conditions, so you'd expect that road surface temperatures would be close to or possibly below zero in any clear spells that do develop. So straight away, this is one example where forecaster confidence in a forecast can be low, because you can see here we've got 4 different models and they're all saying different amounts of cloud. And as I said, the cloud cover is the single most important influence on the road surface temperature. So if you've got different models saying different things, then obviously a forecaster confidence is going to be lower in the general synopsis for the coming day. On this slide, we're going to look at the same model. So we're looking at the model output. On the left-hand side, you can see this is the model output for midday on one day. And then this is on the right-hand side, you've got model output for 6 p.m. on the same day. So you can see the cloud cover is filling in through the course of the day across the UK. Let's put ourselves in this particular scenario in North Yorkshire along the coast. So you can see from the model, if you were looking at this model or a forecaster was looking at this model, you'd expect the forecasters to be something along the lines of giant sunny conditions during the afternoon, followed by clear skies in the evening, and then turning chilly under any of those clear skies as well. So let's look at what the raw road model data would look like for this particular area. So let's say we put a weather station in that area along the North Yorkshire coast. And as you can see, you've got the raw road model data is suggesting in this particular weather setup that the road surface temperature would fall below 0 during the evening under those clear spells or clear skies before cloud cover then fills in from the east. And then you can see that during the later part of the evening, you start to see the road surface temperatures do start to stabilise and recover as that cloud builds. Because as I said, cloud is a blanket to help the outgoing heat, so keep the warmth of the roads. As a forecaster, you're always going to be analysing the different forecast models for the similarities and the differences between the different models. If the models, as I said, are similar, then the forecast is going to have more confidence in the forecast. The forecasters are obviously always looking at the models, but before we issue a forecast, you're always going to look to see what the latest observations are doing as well. So at MetDesk, we have access to the latest, to the most up-to-date satellite and radar imagery. So let's look at the satellite imagery at lunchtime for this particular day. So as you can see from the satellite imagery, we're looking at the UK being overcast. I mean, there are a few breaks in the cloud, but it is pretty much overcast across the UK. Let's look at remind ourselves of what the model output was for that exact same time. So the model output was suggesting that it would be sunny across most of Scotland, northeast England, and also parts of central and eastern England. So already the model is wrong. So this is one of the things that the forecasters can be up against too. And this is where forecaster intervention comes into play. So as you can remind ourselves, the road model output for this particular site in North Yorkshire, you can see that the road surface temperature was falling below 0 under those clear skies during the evening. However, now you'd anticipate that it's going to stay cloudy through the course of the day because it's already cloudy across the UK at lunchtime at the time of issue. So you can see what the forecaster does is they actually lift the road surface temperatures so that it prevents a frost from forming during the evening, because obviously it's cloudy across the UK based on the satellite imagery. So this example highlights one of the main factors which causes forecaster uncertainty, and that is cloud cover. You can get all the other parameters right, but then the forecast can go purely wrong based on the cloud cover itself. So let's look at a couple of mock marginal forecast scenarios we've put together. So before we start looking at those mock scenarios, it's probably best to quickly just go over the definition of a marginal or amber forecast. Firstly, there are three readiness colours. We've got green, amber and red, and these are similarly defined across weather forecast providers. The green and red are the more straightforward of the three readiness colours. A green forecast, I am going to assume that this is what everyone hopes for when they open their forecast, as this does indicate that road surface temperatures are expected to remain above +1 degree Celsius, and therefore no treatment would be required. Whilst a red forecast indicates that road surface temperatures are expected to fall below 0 with a hazard on the road surface such as hoarfrost, ice, snow, freezing rain, and therefore a treatment would be required. Now on to amber, the marginal forecast, and I think the readiness colour that everyone really doesn't want to see when they open their forecast, although probably snow or freezing rain I liked even less than a marginal forecast. But anyway, at MetDesk there are three different reasons that we would issue a amber or marginal forecast. Firstly, road surface temperatures are going to be between 0 and +1 degree Celsius. Secondly, road surface temperatures are expected to drop below 0 but are predicted to remain dry, so therefore no hazards are expected on the road surface. And finally, and this is saved for very low confidence forecasts, we may issue an amber forecast if a road surface temperature drops between +1 degree Celsius and +2 degrees Celsius. And this tends to be related to the variable low cloud situations. Again, I know everyone's favourite kind of forecast. So for the scenarios, we're going to put ourselves in the magical land of Winterland in the middle of winter. So let's say mid-January time. Don't worry, it's not snowing in either of these scenarios. We're just going to be looking at two different marginal forecasts. Now, I'm not here today to tell you if or when you should grit or how much you should grit. I'm just going to go through a couple of scenarios and some useful hints on what to look out for on the forecast. So let's look at the first scenario. We've got a headline that says road surface temperatures marginal and the confidence is high. The forecast of text then reads, it will be dry this afternoon with sunny periods and patches of cloud. During this evening and tonight, it will remain dry with mostly clear skies. Turning chilly with road surface temperatures falling marginal, but they are expected to hold above zero. And then you've got dry and bright conditions tomorrow morning. Then we're going to look at the hourly table for Winterland. So this provides hourly figures for the road surface temperature, the air temperature, the weather type, whether there's the presence of hoarfrost or the presence of ice on the road surface, snow accumulations, wind speed, visibility and precipitation. So the first thing I noticed when looking at this table is that the road surface temperature is plus 0.8 degrees Celsius. And as you can see, it's that cell is also coloured amber to indicate it's marginal. The other thing I noticed is that it is only amber for 1 hour at the end of the night, and that's around dawn time. The next thing I noticed is that road surface temperatures are going to remain dry throughout the 24-hour period as well. You'll see just above or below the snow summary, you can see there is a weather type key, so you can see what the weather type, what each cell is representing for the weather type. So in this particular scenario, we've got dry conditions throughout the 24-hour period. And as I already said, the other main thing that I would have noticed in here is that the confidence level from the forecaster is high. Another thing that might be catching your eye on this forecast is the visibility around 5 p.m. and 6 p.m. On our forecast, if visibility drops below 1,000 meters, our forecast will highlight that cell yellow just to indicate that visibility is low. As the forecast text suggests, there's going to be patches of cloud in the afternoon, so that's probably what that's highlighting there. I'd particularly look out for those on those low cloud and fog formation nights as well. As I said, we're not looking at there being any snow in the forecast. However, if there was, then the forecaster would also mention that. And we offer details here for that. So that would be things like snow amounts, locations, timing, and whether there be any drifting. As part of your forecast, you may also receive site-specific forecast graphs. So let's look at the site-specific forecast graph for this particular scenario. So the black line is the road surface temperature. The blue line is the air temperature and the green line is the dew point temperature. Then underneath the graph you have the surface state. In this scenario, as we've already pointed out, we're going to have dry conditions throughout the 24-hour period. So as you can see, that's lime green throughout. Your gritting decision will come down to your authority's decision-making matrix. So always follow that. Some clients will grit on forecasts that are below +1 Celsius, whilst others will have other elements built into their decision matrix to decide whether they should grit or not. As this is a high confidence forecast with road surface temperatures above zero and dry conditions, there is little risk of a hazard forming associated with this forecast, as roads are dry. And as you can see from this site-specific forecast graph, the dew point temperature is well below the road surface temperature. So even if the road surface temperature drops below zero, there isn't the presence of any moisture on the road surface for a hazard to form. Scenario B, first glance, I straight away look at the hourly table and it's already looking a little bit more colourful than the previous scenario. So my guess is it's a bit more going on. Headline of this forecast is the same as the last one, so road surface temperatures marginal, and we've got a low confidence forecast. The forecaster text then reads, it will be cloudy at times this afternoon with the chance of some light rain or drizzle. During this evening and tonight, it will remain mostly dry with clear spells expected, but also a fair amount of cloud. Turning chilly with road surface temperatures falling marginal, but the cloud should be sufficient to hold just above zero. Dry and increasingly bright tomorrow morning. So there's a bit more cloud around in this scenario in comparison to the previous scenario. Okay, so Then we're going to look at the table. I noticed the road surface temperatures fall into marginal territory mid-evening and then again during the night. So there's two separate occasions in this 24-hour period where road surface temperatures are marginal. As the forecast mentioned, there will be clear spells and cloud around. So the road surface temperatures are dipping into the marginal territory during the clear spells. The minimum road surface temperature is actually the same as the previous forecast. So both of the scenarios that we're looking at have a min road surface temperature of plus 0.8 degrees Celsius. However, as I already mentioned, the confidence in this forecast is low. So the uncertainty is based on the cloud cover and whether the cloud will be sufficient or whether the clear spells will be more prolonged than forecast, and therefore road surface temperatures could fall below zero, or it could fall lower or even below zero than what is expected or forecast to. A couple of other things you'll probably notice. Firstly, there's some precipitation during the afternoon, but this quickly dries out, so probably not something to be too concerned about. However, in the afternoon and evening, whilst the road surface temperatures are marginal, dew is also forming on the road surface. So if the clear spells are more prolonged, then there is the risk of the road surface temperatures dropping below zero and a hazard forming. So if the road surface temperatures fall below zero, this could mean that a hoarfrost could form because you've got moisture on the road, and therefore there's more of a risk associated with this forecast because of that, because the previous forecast there was dry conditions. So here we've got the site-specific graph, and as you can see, slightly different to the previous one. What I'm going to do is I'm just going to pop both the graphs up against each other, and we're just going to have a quick look at the differences in these site-specific graphs, as this helps highlight the risks associated more with scenario B, even though, as I previously said, both forecasts have a min road surface temperature of plus 0.8 degrees Celsius. So first, let's look at the amount of time the road surface temperatures are below +1. Scenario A, road surface temperatures are below +1 for 1 hour at the end of the night. Whilst in scenario B, the road surface temperatures are below +1 for several hours across two separate occasions during the evening and overnight. That straight away suggests to me there is more of a risk associated with scenario B, as road surface temperatures are marginal for several hours, and therefore if those clear spells are more prolonged, then road surface temperatures could drop lower than they're forecast to. Secondly, let's look at the dew point temperature. So as you can see, in scenario A, the dew point temperature, as we previously mentioned, is well below the road surface temperature. Whilst in scenario B, you can see that the dew point temperature is fluctuating around the road surface temperature. So when the dew point temperature drops below the road surface temperature, this will mean that dew will form on the road surface. So in scenario A, we have dry roads, and in scenario B, there's moisture present on the road in the form of dew. The presence of moisture on a marginal forecast therefore increases the risk associated with this forecast, as if a road surface temperature falls lower than expected and does drop below zero, then there's more of the risk of hoarfrost and frozen dew forming on the road surface in scenario B. So that's it from me for now. Please remember, I'll be on at the end for any questions you may have. But now over to Bren, and he's going to talk us through what might be in store for us this winter. Thank you.
Hello to you all. I hope you're all keeping well. My name is Brendan Jones and I'm the forecast manager at MetDesk. Now, MetDesk provide weather forecasts for a range of industries, but that includes, of course, the winter gritting operations from October through to April. And my role as forecast manager is to be heavily involved with that forecasting through the daytime and nighttime for highways authorities or local authorities across the UK, but also to oversee our team of around 20 meteorologists who are all dedicated to not only producing those winter maintenance forecasts, every day of the season, but also monitoring those conditions 24/7. So that includes watching those road temperatures overnight, updating as necessary, keeping everybody informed. Now, speaking of winter forecasts, that's what I'm here to provide for you today. So it's a seasonal forecast that I'm going to look at, which is very different to the usual 24-hour or few days into the future forecast that we provide to the industry. And seasonal forecasting, predicting the winter going forward ahead in time, requires very different skill sets, very different pieces of information. So the agenda for the next 20 minutes or so, firstly, the ingredients used to produce these forecasts, because they are very different, as I mentioned, to the day-to-day forecast that you may see. But also the teleconnections. So that's basically looking at the big global patterns on Earth right now, things like the sea temperatures, the amount of ice around the North and South Pole, and also what the sun is doing, how active is the sun. Those things can have a big bearing on what's happening into the future. We do have long-range forecast models we're able to look at, so I'll show you a sneaky peek of what they are showing for this coming winter. And then finally, once I've introduced you to all the ingredients, I'll actually provide you with what we're forecasting for December, January and February, and then into March and the springtime next year as well. Okay, so without further ado, what is a long-range forecast? Well, essentially, they're designed to highlight trends going forward in time. They're not there to try and accurately represent the day-to-day variation in the weather. We can't possibly do that. If you've got apps on your phone, for example, that are already telling you what the weather is doing on Christmas Day, you should really be binning those, because they cannot be trusted. You cannot accurately represent weather that far ahead. Typically, around about 5 to 7 days in the future is considered to be, accurate enough for hourly by hourly forecasts. But once you get beyond about 5 days or so, really you're starting to look at trends instead. And certainly once you get into weeks or months into the future, you're really looking at trends in temperature and precipitation rather than daily detail. In fact, I've said here at the bottom that seasonal forecasts tend to refer to expectations in terms of the relative to the averages. Now, for the UK, we look at things like temperature and precipitation averaged over a 30-year period from 1981 to 2010. And then our predictions for the summers or the winters are then kind of expressed as sort of whether they are above average or below average in terms of wind and rain and temperature and that sort of thing. That's about the detail really that we can get, but it is still useful for winter maintenance. For example, if you're expecting air temperatures to be below the seasonal normal for a month, whilst at the same time precipitation or rainfall is above the seasonal, that's telling you it's going to be colder and wetter. Colder and wetter, of course, means more ice, more snow, so it could be a trickier month for winter maintenance. So that's the ingredients for producing a forecast. Now, how do we sort of actually go about doing it? Well, there's a number of techniques. The first one is, as I mentioned, the global weather forecast models. Now, this snapshot here on the right-hand side, it's basically showing you the sorts of things that a weather forecaster sees on a daily basis. But these weather forecast models, sort of once a month or so, are projected much further ahead in time, so weeks and months into the future. Now, weather forecasters exercise a lot of caution when looking at these, because we know that weather forecast models can have their faults even hours into the future. That's why we still have human forecasters to try and sort of solve the issues that these models can bring. So there is a lot of caution to be kind of erred with in terms of looking ahead into the future, but nevertheless, they can give useful trends as to what may occur. So we'll have a look at some of those long-range forecasts from the models in a little while. The next thing is ensemble output. Some of you may have heard of these already, but essentially ensembles is a way of taking one weather forecast model, kind of duplicating that dozens, if not sort of up to 50 times or so, changing the starting point of that model a little bit, and then letting it go on its merry way. Now, if you've got 50 weather forecast models all looking at December, for example, if they're all telling you very, very similar things, then you can have a reasonable confidence about perhaps what the month is going to be showing weather-wise. However, if those 50 or so members or forecast models deviate wildly, then that tells you that there's a huge range of possibilities and your confidence is going to be lower. So ensembles are very, very useful. They're actually useful even for looking at the weather in 7 days' time, but they're really, really vital for looking at seasonal timescales. Now, I mentioned teleconnections. That's kind of a developing science, really. It's all about trying to capture what's happening with the world right now. The sea surface temperatures, the energy from the sun, all of the big global weather patterns that occur on cyclical scales of decades, for example. If you can have a look at all of the last time that these sort of the current teleconnections all coincided, what did that mean for the European winter? How did it go? Of course, these aren't foolproof, they're not definitive, but they can, in some cases, be better than the long-range forecast model. So we'll have a look at a few of the more important, the big hitting teleconnections in a few minutes. But perhaps the most important determinant for kind of UK and Northwest Europe is actually, what is the flow doing across the Atlantic? Is it sort of driving in from the west, bringing lots of warm, mild air off the Atlantic, or is it coming in from the east, the snow fields of Russia? So knowing whether it's what we call a zonal or meridional winter flow is very important. So we'll zoom out to space to show you exactly what I mean. If I asked you the question, why is it warmer at the equator? Some of you may say, well, it's because it's closer to the sun, so there's more energy. That's not strictly true, okay? It is a little bit closer to the sun, but the main reason it's much warmer down towards the equator is because the sun's energy has been focused more directly. The sun is overhead, so for every square meter of land, you're absorbing more radiation. In fact, over a year, you're absorbing more radiation from the sun than you're actually losing back to space. Contrast that with the North Pole. And in fact, even our sort of latitudes, you're typically losing more heat to space over the space of a year than you're actually gaining from the sun. So that's why the north is colder than the south. That's why the poles are colder than the equator. Now, in between what we call those warm tropical or cold polar air masses, there's a meeting point, which I've shown in the black dotted line here. Now, that's the meeting point of the cold and warm air, but the air masses don't mix together. They're a little bit like oil and water. If you try to mix them together, they will keep on separating out. And so in essence, you have an almost semi-permanent boundary around the northern hemisphere where the cold polar air sits, refusing to allow the warm tropical air to move its way northwards. Now, if we've got a nice static situation like this, then this is what's called a zonal flow. Now, you've probably heard of the jet stream. It's a ribbon of very strong, fast winds blowing several kilometers above the ground, typically all the way around the northern hemisphere, blowing from west to east. So in our case, coming from America across the Atlantic to the UK. Now, in this situation, if there is a very straight line like this, it tends to allow the jet stream to pick up speed. And actually, the jet stream is responsible for developing and steering those big Atlantic storms that bring us wind and rain. So if you've got a very strong jet stream like this, because of this flat kind of dividing point between the cold air and the warm air, you're more likely to get more storms. And of course, with storms comes lots of warm air. So that typically means less gritting in the winter time. So this is a zonal flow. A very strong zonal flow tends to keep us much, much milder here in the UK. Now, that boundary between warm and cold isn't really that static. It quite often oscillates northwards and southwards. So you have warm air pushing northwards, cold air pushing southwards, but the jet stream still tends to blow along that boundary. Now, of course, the jet stream itself is largely dominant in this case. It actually creates these buckles itself. But these buckles, once they get in place, they can last for several days, if not weeks, without really moving around. And so if you're here on the right-hand side, you can be in a very warm tropical air mass for several weeks. On the other hand, if you're in a cold zone like this part here, then you can be in a much colder flow. So some of our coldest winters in the UK come from these meridional flows, but when we're trapped within this kind of cold pocket here. Think Peace in the East, 2018, we were stuck in this regime for a good couple of weeks or so. So we're really looking at, is the winter going to be a zonal winter, in which case it's probably going to be at least very wet, but probably quite mild as well, or is it going to be meridional? Is there a chance that we could get stuck in one of these blocked weather patterns, and particularly can we get stuck within the cold side of that block? So just to show you what that can mean for Northwest Europe or the Northern Hemisphere, on the left-hand side here, this is the temperature anomaly, so the difference from the 30-year normal for March. And of course, March was the month that contained the two beasts from the east. And these blues and purples here are showing you just how cold it was relative to normal, several degrees below normal across Northwest Europe and Russia. Other parts of the world had much warmer pockets of air where it was coming up from the tropics. So contrast that on the right-hand side with February of this year just gone. It was a much more zonal weather pattern, screaming jet streams coming out of the United States across the Atlantic, piling the warm air, not just into the UK, but also well into Arctic Russia. And you may remember the news stories being carried through the winter. Temperatures across northern Siberia were 20, 25 degrees above the seasonal norm. It was quite worrying, in fact, as to how warm it was up there, because that pattern represented itself through January right through to March as well. And there are signs, perhaps, that might happen again. Signs of a warming world, perhaps, we'll have to see. So that shows you how you can get these big temperature differences between meridional and zonal winter months. But of course, meridional doesn't necessarily mean cold, because you could be stuck in one of these warmer southerly flows. It's kind of just chance, really, as to which side of that jet stream you actually get. Okay, so teleconnections, let's move on to these now. So there's a number, well, in fact, there are hundreds of teleconnections, but the most important ones really are what we call Arctic sea ice, the solar cycles, More complex names, the quasi-biennial oscillation, and also ENSO. Now, you've probably heard of El Nino. You may not have heard of La Nina, but that could be a big hitter for this coming winter in terms of what we might see in the UK. So firstly, Arctic sea ice. Now, this graph on the right-hand side here shows you the extent of how much of the sea around the Arctic is frozen during the course of a year. And of course, the warmer the weather is, generally the less of that sea ice will actually be there. And as you might expect, through the summertime, the amount of sea ice in millions of square kilometres drops away, typically reaching a minimum point around about September before the temperatures start dropping, the sun gets lower in the sky, and your ice starts to reform. Now, this grey dark line here is the 1981 to 2010 average for sea ice, which typically bottoms out at around about 7 million square kilometres of ice around the North Pole in September. Now, pretty much all of that average 30-year period has been sitting above where we've been over the last 10 years. Whether or not you believe in global warming matters really not on this graph. The fact of the matter is here is that Arctic sea ice over the last 10 years or so has been well below the 30-year average prior to that. In fact, 2012 was the lowest extent on record. 2020, this year, hasn't been far off that, so we've been right down towards the bottom end. But crucially, if you look at the rising limb here as the sea is now beginning to freeze, it's now at a record low as we head in towards sort of early to middle part of November, because that water off the north coast of Siberia, where it was very warm through the winter and through the summer, it's just not been freezing very quickly, and that does have big feedbacks. So October 2020 had the lowest Arctic sea ice on record. And why does that matter? Well, it's because more open water absorbs more of the sun's radiation. Even in the winter, the sun's strength is still being absorbed. If you've got lots of ice and snow cover, it's what's called a high albedo. It reflects the radiation back out to space before it gets a chance to bed itself down on the Earth. But if you've got lots more water, it can absorb that heat. And so that lag, that heating goes on and on really until you can eventually start to form some ice. What that does favour is higher pressure forming over parts of northern Russia, and that higher pressure can have a big influence around the whole globe, causing a more blocked or meridional pattern. And in fact, that's probably one of the reasons why we've been so mild and unsettled through October and November so far. Meridional doesn't mean cold, remember, it just means you get stuck in ruts. And of course, for most of the autumn so far, we've had sort of relentless wind and rain, largely because we think of this meridional pattern, meaning that we're in the kind of warm tropical part of that. I have to say now that the Arctic ice is now starting to form, this teleconnection will have a lesser bearing, I think, as we go forward. But nevertheless, what's happened so far this winter has already been determined, I think, by that sea ice extent. Now, the next thing is sunspot activity. Now, you may not have heard of sunspots, but they're essentially very highly energized portions on the sun's surface. And the sun goes in an 11-year cycle where those sunspots increase in number and then decrease again every 11 years or so. And it's pretty uniform, although the actual peaks and troughs tend to differ. But essentially, when you've got lots of these sunspots, the amount of radiation coming down to Earth, the solar storms, if you like, increases. And what that tends to do is power up the atmosphere, power up the jet stream. So typically, these peaks here, you can see the number of sunspots. When you're at the top of those cycles, you tend to get a more energized atmosphere, meaning lots more kind of Atlantic-driven systems. So typically speaking, high sunspot years are those winters where we've had very few sort of major cold spells. Usually they're very, very mild winters. Now down the bottom end of these is what we call the solar minimum, the solar troughs. And if you go back through all of your sort of memories to the coldest winters you can remember, perhaps not in the case of all of you the 1947 winter, but that was down at the very bottom end of the solar cycle. Many of you probably heard of the 62-63 winter, which was extremely cold. That was also down the bottom end of that cycle, as was the winter of 1987. And much more recently, of course, the winter of 2010, the coldest December on record. That was down towards the bottom end of that cycle as well. Now, our kind of most recent solar cycle is this one on the right-hand side here. Very low solar peak, I have to say. The numbers of sunspots are very low at the moment as a peak. But of course, the beast from the east, 2018, you can see there was occurring towards the bottom. The last sort of 2 winters or so have been a lot milder. However, we're still near the bottom of that solar cycle. We're still in that zone where we could have some colder outbreaks as a result of low solar spots. So that's something we have to keep an eye on. These blocking weather patterns may be more numerous again this winter as a result of solar cycles. Now, 2 more things to look at. Firstly is the QBO, the quasi-biennial oscillation. Without trying to get too technical here, this is basically where the wind high up in the stratosphere around the equator basically changes direction completely, sort of anything between sort of 10 and 15 years or so. And what you're seeing here on this graph is the direction of the wind. So if it's red, it's blowing from the west. If it's blue, it's blowing from the east. And you can see there's this regular cycle that goes on. The easterlies tend to be stronger in magnitude than the westerlies, but this cycle nevertheless has been ongoing until very recently, where we've had some strange behavior. So you can see here from 2015 to 2017, we had a double positive really, with very little in the way of easterly flow. We then did get an easterly, but then more recently, over the last 12 to 18 months, we've almost had another double positive as well. So this winter originally was looking like we were going to go into this negative phase, this easterly wind, but actually it now looks like we're going back into a positive QBO again, with the winds blowing from a west. What does that mean for the weather? Well, easterlies tend to encourage something called sudden stratospheric warming. That is when the very high altitude temperatures above the North Pole suddenly warm up 50, 60, 70 degrees over the space of a few weeks. That can be encouraged by easterly QBO. And when you do get those very strong stratospheric warmings, it can create more blocked weather patterns to increase the risk of getting cold weather in the UK. So the fact that the QBO is now looking to be more westerly is perhaps favouring the idea of a reduced risk of this blocking pattern, a reduced risk of stratospheric warming, and therefore reduced risk of big cold easterly outbreaks. And as I mentioned, QBO was largely positive in 2018 and 19 as a result. And of course, that winter was relatively mild. We didn't get too much in the way of snow or ice. Okay, so the final one I'm going to look at is La Nina. Now, you've all heard of El Nino, I'm sure. El Nino is basically looking at the temperatures across the Pacific. And so this graphic here is showing you the sea surface temperature anomalies. Where it's red, it's much warmer than normal. And when it's cold, when it's blue, it's much colder than normal. Now, this was the record-breaking El Nino from a few years ago. You can see that off the west coast of America, the sea was much warmer here. Whereas towards the western side of the Pacific, near Indonesia and Australia, the sea was a little bit colder than normal. These kind of situations where the eastern Pacific is very warm is called El Nino. Now this year, we're looking at something called an El Nina, and that's basically the exact opposite. And as you can see here, here's the projection for sea surface temperature through October. Much colder than normal off the west coast of America, much warmer than normal off the east coast of Australia and Indonesia. So what does that basically mean for us? Well, there's lots of scientific literature out there to kind of almost contradict itself, but what it tends to mean when you've got this strong La Nina is that through what's called the Q4, the first half of winter, so December in your case, it can lead to, generally speaking, more kind of blocking weather patterns. So December could see more blocking patterns, increased risk of cold because of this La Nina. But on the other hand, it then also through Q1, January, February time of the year, can actually encourage now more zonal flows coming in from the west. So this teleconnection on its own would suggest a more blocked December, but also a much more zonal or sort of milder January and February. I have to say, though, it does generally influence conditions in the Pacific countries rather than Northern Europe. So here's a look at all the teleconnection I've just been through. This low sea ice can promote early blocking, especially during the autumn and into December. The solar cycle itself is right at a bottom end at the moment, so that really does indicate a greater risk of some blocking, some colder weather. But the positive QBO, that supports more of a zonal flow, and in fact the La Nina at the current stage as well, that does favour zonal overall, but it can indicate a more blocked December. So a little bit of confliction here with the teleconnection. So, but I have to say, sort of erring towards this idea of blocking perhaps to begin with, going more zonal through January and February. So we're just going to have a quick look at these forecast models now, the second ingredient, because these might help us out. And this is the most recent ECMWF seasonal model. And this is looking at the temperature anomaly for the entire winter. So December, January and February. The oranges and reds are where the temperatures are expected to be well above normal, blues are well below. And you can see for the winter as a whole, the UK is kind of near normal, perhaps urging towards slightly above normal. But look at Scandinavia and Northern Europe, you've got incredibly high sort of temperature anomalies up there. Perhaps another worrying sign perhaps of what we saw last winter of reduced sea ice and things up there as well. But to break it down into the kind of the individual months, you can see on the right hand side here, December, across the UK is actually close to being slightly below normal in terms of the temperatures, whereas January and February, you can see those yellows are starting to come back. So this ECMWF model supports the idea of kind of lower temperatures with respect to normal and perhaps more blocking in December, and then generally speaking going a bit more kind of westerly orientated again through January and February. So in terms of the pressure patterns, you can see here that this is kind of showing you the 3-month likely pressure patterns. Now, when you've got low pressure to the north and high pressure to the south, that's when you get your strongest westerly winds. So the lower the pressure to the north and the higher the pressure to the south, the stronger the westerly winds will be. And this is the pressure anomaly. So the blues are showing you where pressure is likely to be below normal for the winter as a whole, and then down to the south, the yellows are showing you where pressure is likely to be higher. So for the winter as a whole, it supports this idea that it is going to be westerly dominated. But of course, as we've said, that's probably going to be weighted towards the back end. So what about MetDesk winter forecast? So here we go. We favour at the moment that that for the winter as a whole, the temperatures are likely to be probably a little bit above the 30-year average. However, I think that's looking at the 3 months, December, January, February overall, and that's down to a more dominated westerly flow pattern. But as I've already said, we think that the cold is likely to be front-loaded this winter. What we mean by that is that if we're going to get cold spells, more prolonged cold spells, we think December is the month that's most likely to happen. Of course, that's not to say that you won't get some snow and some ice in January, February, and even into March, but we think that relative to the seasonal average, December has the strongest chance of seeing more blocked patterns and more cold. Now, we think that January is probably going to be a transition month. So it may well start off cold, kind of an overspill from December, likely turning a bit milder as time goes on. And then February, probably the most zonal month of the winter, more dominated by westerlies with more wind and rain. So I think winter maintenance possibly more tested during December than it will be in January, February. But one thing to say here, of course, is that even in mild winters, all winter months can see wintry weather. Some of our biggest snowstorms in recent years have not kind of necessarily come from the beast from the east. They've just come from one or two, cold spells that last a day or two, because that's all you need. Low temperatures and some precipitation, you can get a big, heavy wet fall of snow to cause you problems. That's not what we're talking about here. What we're looking at is the overall trends. December likely to be colder, and then January, February, relative to normal, likely to be a little bit milder. Now, going into March and April, it looks as if pressure is going to be slowly building, perhaps slowing down the Atlantic jet stream, but the weather forecast models at the moment are hinting that despite that kind of increased risk of blocking through March and April, temperatures are likely to still be near or slightly above the seasonal norm, so perhaps no really late cold spells like we had in 2018. Okay, that's probably more than enough information for everyone listening today. So thank you for taking the time to listen to our seasonal forecast. Of course, those of you that speak to us on a daily basis can continue to monitor how this goes. But what I'm going to do now is hand over to my colleagues, Richard and Cassie, in case there are any questions forthcoming based on our presentation. Thank you very much.